Hello friends, let's review our design so far for matching engine in which we are using one-dimensional data structure for linked list and priority queue. For adding any order to linked list and priority queue, we have seen in this table that for linked list it takes O(n) of log n, and for priority queue is O log n. So in this case, as is obvious that priority queue is better data structure for adding any unfilled order. So for linked list, as we know that when we are adding the order to the order book, so what it means is that we are having buy orders and sell orders, both are linked list. So adding it to the last is fine, but when we have to compare it and sort it based on the price and time priority, there where it's going to take O of n log n. So sorting is the real thing that which is actually causing this this algorithm to give the time complexity of O of n log n for linked list. But for priority queue, when we try to add the order to our priority queues, we know that adding anything to the priority queue and then sorting it based on the price and time priority, it is only going to take log n of time. So that's why priority queue is better for adding the order and then sorting it based on price and time priority. Now let's examine about the matching part. As you have seen that for matching, linked list only takes O(n) as well, but for priority queue, it takes O(n) of log n. So in this case, for the matching part, linked list performs better than the priority queue. Now for matching engine, for our matching orders for linked list, now we have seen that that we always go to the while loop for the opposite order, opposite side. So if I receive a buy order, I'll see that in the opposite side of sell orders, what are the prices which can match. So this will be in the while loop, and whenever the price is matched, in that case, we only call this get first method, which is the top of the head of the linked list, which is always O(1). And then we match it. And if the quantity has, if the whole quantity has been used for the cell, then we have a match. Then we remove it from the first. Even for the remove first, as you can see, it's O(1). So the overall time complexity, if we keep on iterating until we are finding the match, it would be O(n) here because it's a while loop. And for each operation, we are only using O(1). So O(n) multiplied by O(1) would be overall O(n) of time complexity for linked list for matching orders. But if we compare the same for the priority queue, in that case, we are again going to the while loop, and whenever we find a best opposite matching order, in that case, the peak method will give me O(1). But as soon as we exhaust the whole quantity of that, we have to remove that from the opposite order. And this removal, the pole method, it will take log n. So this is where it moves from O(1) to O of log n. And because this is a while loop, it will keep on continuing for the best matching order from the opposite side. And every time it pulls it out, it will take an additional of O log n. So that's why the overall time complexity would be O(n) multiplied by O of log n. So the overall is n log n for priority queue. Now for cancel, we see that both linked list and priority queue have got O(n) of time complexity. So in this case, both are same. So now we see that addition, linked list is worse than priority queue, but for matching, linked list is better than priority queue. But for cancellation, we can see that there is almost the same. Now, as we have discussed previously, that for cancellation order, we'll first of all remove the order and then add it. That was for MN. For cancellation, we are only going to remove it from our cache as well as from our linked list for buy order or for the sell order list. So remove order is very straightforward. First of all, we will remove from the cache, which is O(1), and then when we try to remove it from our linked list of buy orders or sell orders based on the side, then it will iterate from the head to the tail to find that order first, and then only it will remove it. So that's why this remove on linked list would be O of an operation. So again, for the priority queue, if I go back, the priority queue has also got the same thing. We are first going to remove it from the cache, and this buy orders and sell orders are priority queue, but for the remove operation for priority queues are also O of n. So that's why it would be ON for both priority queue and linked list for cancellation of an order. Now for amendment of orders, we can see that for linked list, it takes O of n log n, but for priority queue, it's ON. So this is where priority queue is again wins over linked list. So for amendment, as we have seen that whether it's for quantity or only for price or for both quantity and price, it will remove the order first and then add it back. So for removal, as we have seen that the cancellation would be like same as removal. So it will take ON, but while adding it back, we have seen that it is taking n of log n. But for priority queue, it was only log n. So that's why for amendment of orders, priority queue is better because adding it back only takes O log n here. But for linked list, it takes n log n. That's why the overall time complexity is like poor for linked list for amendment of orders. Now in the code, as we see that for linked list, for the amendment of orders, quantity, price, whatever, we remove and add order. This we call this method. And when I go to this method, the removal of order from a linked list, it takes ON. And for adding an order back, because remember that we are going to like sort it again, and sorting in linked list will take n log n. So that's why the overall time complexity would be n of log n. But for priority queue, addition of order to a priority queue is O log n. That's why the overall time complexity would be only ON, which is the worst of this. So ON plus O log n is ON. So guys, we have seen that using like one dimensional data structure, if you are using priority queue, so there are few methods which are like better for priority queue, but only except for order matching. So just like reviewing this, I mean, we can see that if we can combine both priority queue and linked list in a 2D data structure and redesign our whole matching engine, will that give us a better solution? So this is what we're going to discuss in the next video.